Hey there. So, in this next example problem, I just want to talk a little bit about impulse. It's not something that I really mentioned in my talks about momentum, but I think we can discuss it thoroughly through example. So, in this situation, we just have a block of mass m, and it has a net external force of Fx pushing it to the right. Now, the key with Fx is it could be any function of time. So this is a variable force that is pushing the block to the right. So for part A, we want to derive a general expression for the block's momentum as a function of time. And for part B, given a specific graph of what Fx looks like, right? Part A, we have no idea what this force looks like. Part B, we're given a graph of what Fx looks like as a function of time. And we want to find the change in the block's momentum over the 6 seconds. All right, let's go ahead and start by addressing part A. So for part A, we want to derive an expression for the block's momentum as a function of time. So remember, generically, we already proved that the net external force acting on a system is responsible for the rate of change of that system's momentum with respect to time. That's what that statement right here means. So we have a one-dimensional problem, right? We only have our force acting in the x direction. I can go ahead and drop my vector symbol because of this. This is just an fx problem. And so same deal with my momentum. My momentum's only going to change in the x direction as well, so I can drop the vector symbol on that. All right, so we can either find my momentum as a function of time, or I could find the change in my momentum between two time points. To go with route 1, we'd have to use the indefinite version of an integral. To go route 2, we'd have to use the definite version of an integral. This problem, of course, is asking for the purple, right? A general expression for the block's momentum as a function of time. So we're going to somehow be using this root here. So this is a separable differential equation, so I can move my dt to the other side, and then I can integrate both sides. Remember, indefinite integral because we're just finding the antiderivative here. And so, oh, whoops. And so we would get that this guy here, this is just px as a function of time. And we get that my momentum as a function of time is just the indefinite integral of my force with respect to time. This is a very just simple manipulation of a differential equation. Okay. So now for part B, suppose we have a graph of fx that looks something like this. It's some arbitrary shape here. We have time on our x-axis and we have our force on the y-axis. We want to find the change in the block's momentum over the 6 seconds. So in order to do this, we're just going to rewrite our same differential equation from before. Remember how I said there's always two routes that you can go once you have a differential equation. You can find some general expression using an antiderivative, or you can find a change in the momentum in this case between two time points via a definite integral. So all we have to do is separate this out. And now because I'm interested in my change in my momentum, I'm going to use the definite integral from 0 to 6 seconds. Okay, this integral from p final to pi, that's the definition of delta px. And then all I need to do now is solve this integral here on the right. And remember, the definition of what a definite integral is, that's just the area under my curve between points t equals 0 to t equals 6. So let's go back to my curve and let's figure out what that area is. This first triangle here is going to have an area of 1/2 times its base, which is 3 seconds, times its height, which is 30 newtons. This rectangle, just take the length times the width, so 2 seconds times 30 newtons. And then here, my last triangle, we have a base of 1 second and a height of 30 newtons, so 1/2 times 1 times 30. We sum all of these shapes together to get the total area, and we get 120 Newton seconds. And then as a fun exercise with dimensional analysis, you can verify that a Newton second is in fact a unit of momentum, um, which is what we would hope for because we're just trying to find a change in momentum uh, over the course of the 6 seconds. So that's all that we did. Our result, we found that our box's momentum changed by 120 Newton seconds over the 6 seconds. Now, we can introduce a new definition that the change of momentum, in this problem it's in my x direction, that's defined as the impulse delivered to the box in that 6 seconds. We call this impulse. So we could also read this same statement from above as the box had an impulse of 120 Newton seconds applied to it over the 6 seconds. So an impulse is really just a fancy way of saying a change of an object's momentum. Um, so yeah, there we go. Pretty quick problem. Just messing around with differential equations. Very nice, easy, separable differential equations. And basically rewriting it in different forms that, are very useful. So with that, I hope you enjoyed, and thank you so, so much for watching.